Hello again, everybody. Thanks for being back. It's my pleasure to be here again. So let me get my screen shared here. All right, so today we're going to continue talking about shadowing and dynamical systems. Today our focus is going to be on a way in which the shadowing property can inform us about other dynamical notions in dynamical systems. All right, so there's going to be a few things on this presentation that are going to be a bit review. We'll go through those pretty quickly. So again, for those of you who maybe weren't here yesterday, a dynamical system for our purposes is going to be a function, a continuous function on a compact metric space. The thing we're most concerned about today is, well, a thing we are concerned about today is the orbit of a point, which we're going to think about as the sequence x, f of x, f squared of x, f cubed of x. All right, so just a quick motivating example. Think about the map f from the interval to the interval, given by this formula here. So the graph of this is something that I would like to be able to draw. Why can't I draw on this? Sorry. There we go. Okay, so the graph of this is something like this, where this is the point 1/2, slope 2, and slope -2. So the idea here is this is a function. This is a very important function in terms of an example called the slope to tent map. And it has the property that has a lot of great properties. But let's think about a particular initial value. Let's think about x equals 1/28. That's about here on the number line. That's 1/28. Okay, if we start iterating f on that, we'll get 1/14. Then we'll get 1/7, 2/7, 4/7. And then 4/7 becomes 8/7. Well, 2 minus 8/7. 2 minus 8/7. Anyways, we go through this and we get this situation here where for some number of iterates, we have this cycle like that. Okay. And so the idea that I want to talk about today is the long-term behavior of orbits, more than just the full picture. In that particular example, the orbit settled in on periodic orbit 2/7, 4/7, 6/7. So you go 2/7, 4/7, 6/7, 6/7 maps back to 2/7, and a cycle. Okay. So as a matter of fact, in this particular map, there are a whole lot of points that have this same specific, what you might call long-term or asymptotic orbit picture. Okay. So the question I want to address today is, what can we say about the asymptotic behavior of the orbit of a point in the system? All right, so a particular notion that we're going to talk about today, this is the main focus of today, is the notion of the omega limit set of a point. So the idea here is we take a point x in our space, and then we look at the set of all forward orbits, the forward images of it, for some minimal n. So we start out by looking at the collection, the whole orbit as a set. We take the closure, and we start tossing out initial points. We let the n start increasing. Okay. So we look at the x, f of x, f squared of x, on and on, close that set. Then we look at, chop off that first x. Now we just look at f of x, f squared of x, f cubed of x, close that set, intersect this down. This is called the omega limit set of x. There are lots of great characterizations of this. It's the collection of limit points of the orbit as a sequence. But some great properties of the omega limit set of a point. Some of the great reasons to think about this is these are non-empty, compact, and invariant. And when we say invariant for the purposes of today, that means that the image of the omega limit set of x is just equal to that same omega limit set. It follows, this follows pretty much immediately from the definition here, because we hit f with omega of x. We know that f and intersections play reasonably well together, especially for nested things, and we can get that through pretty easily, provided f is continuous. Of course, there's a little bit more to that, but not much. Now, an auxiliary notion, a related notion, we're going to talk today about the omega limit set of a sequence. Okay? So here we're going to take a sequence xi and x, okay? And we're going to look at the omega limit set of that sequence, and we're going to do the same thing that we did with the omega limit set, okay? Except instead of having the iterate f of xi, we just have the ith term in our sequence. Okay. So this notion here has nothing to do with the dynamics. It's just a strictly topological idea for a given sequence. Okay? And as such, you know, we expect it to not have much to do with the dynamics. So this notion, the omega limit set of a sequence, well, it's still a nested intersection of compact non-empty sets. So it is non-empty and compact, but it's almost certainly not invariant, right? If xi is just some random sequence, then we don't expect it to have much to do with the dynamics. All right, so there's some preliminary notions. All right, so just really quickly, let's look at maybe just another point. Let's look at x equals pi over 4. If we look at x equals pi over 4, this is some approximation of what the orbit might look like. But then you start peeling off the first couple of things and you get something that looks more like this. Okay? And then you might want to peel off more initial terms. And it's really, really hard to get a picture of what that omega limit set is, right? What is omega of pi over 4? It's really a tough question to address. So what we'd like to do today is kind of ask a slightly different question. Instead of saying, given a point x, what does the omega limit set of x look like? The question I want to address today is, given a subset of x, is it the omega limit set of some point, right? So given a subset of x, is there a point x in x with omega of x equals a? And that's the question we're going to address today. And the notion of shadowing from yesterday is going to come into play pretty quickly here. So some first priority concerns, of course, if A is to be an omega limit set, it needs to be closed, it needs to be invariant, it needs to be non-empty, but that doesn't get us very far. So the idea that's going to bring us together with this classification and with shadowing is the notion of internal chain transitivity. Okay. So non-empty closed set, so we're assuming that a set is closed here. A is internally chain transitive, which we abbreviate ICT, with respect to a function f, provided that for any points x and y in A and any positive number epsilon, there's a finite sequence zi in A that starts at x and ends at y, and that almost follows the dynamics of f. Right? We see that this looks a lot like a finite version of a pseudo-orbit. All right, so that's kind of what we're going to think about today. So sort of the idea is we might have a set A, let's label this A, and we have 2 points x and y. We ought to be able to chain from one to the other, right? This is called a chain, it's called Epsilon chain, right? And maybe for a given epsilon, it takes only 3 steps. But for a smaller epsilon, it might take far more steps. Okay. The set A would be internally chain transitive if given any A, any x and y, and any epsilon, we can find some chain of some length. Okay. So this is, of course, very related to the notion of chain transitivity, which is a related property for the full space, but internal is a property of a subset of the whole space. All right. So it is not difficult to show that every omega limit set is internally chain transitive. Okay? And the way we might do that is by looking at essentially the orbit of our point settles in on that omega limit set. So a schematic of this proof might be something like this. You have this represents omega of x, okay? And then you have the orbit of x settles in on this in a way that kind of fills it up as you go. Okay, so we'll leave off there. So if I want to connect a point A to a point B, I know that A is pretty close to Fn of x for some large n. Okay? And I know that B is pretty close to Fm of x for some large m bigger than n. Okay? Which means that if I think about that, A, I can associate with Fn. I can get from Fn to Fm with an orbit. And then if I come in and make a small jump onto the omega limit set, I can get a picture that looks a bit like this. So I have, here's Fn of x. It maps exactly to n plus 1 of x, which let's imagine we only have a few steps in our process here, and that maps to Fm of x. Well, if I then take, get a different color here, my chain in A, I take a point that's way too big. I'll leave it that way. Take some point here that's pretty close to my little orbit pieces here. And uniform continuity and being able to limit in there and get us where we need to be. So that's something that we can go into more detail about later if we like, but let's just keep it as a sketch right there for now. All right, so let me get that. Okay, so onward. All right, now there are in fact many systems in which every ICT set is also an omega limit set. In a very real sense, most maps of the interval, the shifts of finite type that we talked about yesterday, and lots of other systems. But in general, for a general dynamical system, there are ICT sets which are not omega limit sets. And we're going to look at some of these today. So among others, the identity map on the interval, for example, we saw yesterday that the identity map on the interval didn't have shadowing. Okay? We can see pretty easily that the identity map on the interval has the property that every omega limit set is a singleton, because the orbit of every point is a singleton. But because of the connectedness of the interval, we see that the whole interval is itself ICT, right? So there are definitely situations in which the ICT sets are not coinciding with the omega limit sets. All right, so the question that we're going to start today with is, are there conditions on the map F under which the idea of internal chain transitivity completely coincides with the notion of omega limit sets? Okay. And of course, if the answer to that question was no, this would be a very boring talk. So of course, we expect the answer to be yes. So let's see how this is going to go. So let's remember shadowing. So this is, we talked about this yesterday. If for every epsilon greater than 0, an epsilon pseudo-orbit is a sequence of points x1, x0, x1, x2, x3, such that f of x is close to xi plus 1. Okay? And we say that map F has shadowing, provided that for every positive number epsilon, there is a positive number delta, such that every delta pseudo-orbit is epsilon shadowed. Okay? So that was what we talked about yesterday. Okay? And we say that the orbit as a sequence epsilon shadows the delta pseudo-orbit xi. All right. So this is, it used to be a conjecture, it's now been addressed, but a conjecture that was made when this was first being studied was that perhaps the ICT sets coincide with the omega limit sets. And this was witnessed by Andy Barwell, Chris Good, and Gareth Davies for maps with shadowing. So they made the conjecture that if F had shadowing, then every internally chain transitive set should be an omega limit set, and vice versa, okay, which turns out to be almost true. So we're going to work through the answer to that conjecture here coming forward. So a little bit more material is necessary before we get there. So given a compact metric space X, we can define the hyperspace of compact subspaces, which we call 2 to the X. This is the collection of non-empty compact subsets of X. And it has a natural metric called the Hausdorff metric, where we declare the distance between two compact subsets A and B to be the maximum of the supremum of the infimum of D and AB as A and B range over A and B, and the supremum of the infimum of the other way around. All right, so that's a lot of things built in there. The picture is fairly nice. So if I have, let me get a different color pens here. All right, so if I have a set A here in green and a set B here so A is in red, B is in green, B is in green, sorry. Okay. Then we would want to look at the distances here, and we'd see that there's a point here that's pretty far away from there. Okay. But there are also points in here that are pretty far away from there. So because we're taking that maximum, we're taking the maximum of all of these distances. How far away a point from A is to a point in B, and also how far away points in B are to A. So this metric on the compact spaces, we can work with pretty straightforwardly with a little bit of effort, a little bit of practice. We see that this is indeed a metric, okay? And it has the property that the space 2 to the x is compact with respect to this metric, which is really useful going forward. Okay, so a little bit of notation for what we're about to talk about. We're going to use the symbol W of f to refer to the collection of omega limit sets of f. Right, so we know that for a function f on a compact metric space x, every omega limit set is a compact subset. So every omega limit set is an element of 2 to the x. And W of f is the subset of 2 to the x that's exactly those things. Okay? We're going to use ICT of f to be the subset of 2 to the x, which contains the non-empty closed internally chain transitive sets. Okay? And because of the things we've just talked about, we know that W of f is a subset of the ICT sets of f, is a subset of 2 to the x. Okay. And we'd like to explore this relation here. When is that equality? All right. So this is a theorem of myself and Brian Rains, a colleague of mine here at Baylor. and our theorem was that if f from x to x has shadowing, then the sets W and ICT coincide if and only if W is a closed subset of 2 to the x. Okay. So that's the theorem. We're going to work through a proof of this, and then we're going to kind of go and see how far we can get pushing that a little further before the hour is up. So we're going to talk through a proof of this, okay? And then we'll see where we go. Okay. So a quick outline of what we're going to do before we do anything. First thing we're going to show is that ICT of f is a closed subset of 2 to the x, okay? And that's going to tell us that, and then we're going to prove, that if f has shadowing, then the closure of W is equal to ICT. And that'll tell us that if W is equal to ICT, W is closed, and if f has shadowing, and W of f is closed, then W of f is equal to ICT of f. So our plan is to prove these two lemmas, and our result will follow pretty much immediately. All right, so let's first prove that the collection of ICT sets is closed. All right, so what we're going to do is prove that the collection of ICT sets contains all of its limit points. All right, so let's take C1, C2, C3 to be a collection of ICT sets that converge to a set C, which may or may not be ICT. All right, so we have C1, which is ICT, C2, which is ICT, C3, and they limit to something called C, and these are all ICT. And this one is maybe ICT. Let's see if we can prove that. All right, so in order to prove that something's ICT, we need to take 2 points in that set, fix an epsilon greater than 0, and we need to build a chain from the one to the other. So if this is C, here's A, here's B, and I'd like to be able to get from there to there with a chain with small gaps in it. Okay, and we're going to use the same sort of techniques that I addressed, or at least alluded to earlier, when we proved that an omega limit set was ICT. Because what we're going to do is we're going to take those limiting things, which are ICT, we're going to find one that's close enough and take the chain there and push it onto C. Okay, so let's buy uniform continuity. So f is continuous, our space is compact. We can appeal to uniform continuity to choose a delta such that if the distance between 2 points is less than delta, then the distance between their outputs is less than epsilon over 3. And then without loss of generality, we can just work with delta less than epsilon over 3 as an extra condition, right? If delta, we chose a bad delta, we can make it smaller and it still work. So we have the epsilon, which is our tolerance for our chain. We're choosing delta by uniform continuity. Okay? And then we know that the C sets converge to C, and so we can choose a K so the Hausdorff distance from CK to C is less than delta. Okay, so we have C down here, we have CK, and because that Hausdorff distance is what it is, we know that every single point, let me make these pens a bit smaller, every single point here is less than delta from at least one point in here, right? And vice versa. All right, so CK is a very good approximation of C. All right, so where do we go from there? All right, so where we go from here is we choose some A prime in the ball of radius delta around A intersected with CK, right? So we had C, and we have A right here, and we had CK. Now these are probably not actually intervals, but I'm drawing them as intervals. They're probably very disconnected sets, right? So then we take the ball of radius delta around A, and we choose A prime right there. We do something similar with B way over here, choose B prime right there. Now because CK is internally chain transitive, I can get from there to there, to there, to there, to there, to there, with some small gaps in here, right? Whatever size I need. Okay. And then I'll just take those things and send them back and pick my points down here that are going to be the chain in C. All right, so since CK is internally chain transitive, we can choose a chain, let's call it X naught prime to Xn prime, to be an epsilon over 3 chain from A prime to B prime. Okay, that was the picture we just drew. Okay. Then we're going to chain X naught to be A, Xn to be B, and we're going to choose an Xi in the ball of radius delta around Xi prime intersect C. Okay, so we start with A, we choose a point in CK that's close by, we choose B prime, find our chain in CK, and then we just move that chain right back to C. Okay? And then just chasing the triangle inequality through uniform continuity tells me that the distance between consecutive elements of our chain, so this should still be prime there, is less than or equal to epsilon over 3 plus epsilon over 3 plus epsilon over 3 is less than epsilon, right? And so C is in fact internally chain transitive. Thus, ICT of F is closed in 2 to the X. All right. So that was our first lemma. Okay. Now, because ICT of F is closed and properties of closure, I know that W of F is a subset of ICT of F. And so W of F closure is a subset of ICT of F closure, but that's just equal to ICT of F. And so we get this result here. The closure of the collection of omega limit sets is a subset of the ICT sets. All right. So how do we establish that the closure is equal to the ICT sets? Well, the idea is we're going to take advantage of this notion that was first developed by Barwell, Andy Barwell, Chris Good, Piotr Pro, and Brian Rains to construct what we call an asymptotic pseudo-orbit in C, whose omega limit set, and this is the omega limit set of a sequence, not related to dynamics, is equal to C. Okay? And the way we do this is we take an ICT set C. We pick, let's say, some dense set A1, A2, A3, A4. We choose an appropriate countable dense set. Choose a countable dense subset of C. Such a thing exists. Okay. And then what we're going to do is we're going to take each of these, and since C is ICT, I can chain from A1 to A2 using size, say, a half chain. And then I can go from A2 to A3 using a size 1/4 chain. And then I can go from A3 to A4 using a size 1/8 chain. And then I can go from A4 to A5 using a 1/16 chain, and so on and so forth. And what we end up with is a pseudo-orbit in the sense that the distance between f of xi and xi plus 1, this thing goes to 0 as I goes to infinity. So that's what we mean by asymptotic. Okay? And if we've chosen this carefully, this sequence, this asymptotic pseudo-orbit, will always have the closure of its orbit no matter where we start equal to c, and it will fill up c. So that right there is our starting point. So observations here. For any delta greater than 0, there's some point in that pseudo-orbit beyond which that infinite pseudo-orbit is a delta pseudo-orbit, right? So if I wanted to say find this to be an 8th pseudo-orbit, if I started here at A3, it would be a 1/8 pseudo-orbit beyond that. If I started here at A5, it would be a 1/32 pseudo-orbit beyond that. Okay, so we can always go far enough in that it's a delta pseudo-orbit for whatever delta we like. Okay. So let's fix an epsilon greater than 0. Now we're going to use shadowing. All right. Since f has shadowing, we're going to choose a delta greater than 0 such that every delta pseudo-orbit is epsilon over 2 shadowed. Right? Since shadowing, we can do this for any epsilon. Let's do it for epsilon over 2. Okay. So in particular, what we're going to do then is we're going to choose a point z in x such that f to the I of z, epsilon over 2. So the sequence here shadows xi plus m delta. All right, so xi plus m delta was chosen so that xi plus m delta is a delta pseudo-orbit. So we can find a point fi of z, which epsilon over 2 shadows it. Okay. Now, if I look at this and I look at the omega limit set of fi of z, the omega limit set of the omega limit set of z here is essentially the same as the omega limit set of xi plus m delta, okay, which is going to be equal to c. Okay, so that's our next step, is because the orbit, the actual points here, fi of z is close to xi plus m delta. That means that the omega limit set will be close to the omega limit set, and that was equal to c. All right. So for any a in omega z, we can find a sequence n sub I, natural numbers, such that fn I of z approaches a. Right? That's because the omega limit set is the collection of limit points of the orbit. Okay? Without loss of generality, the sequence xni plus m delta converges to some b in my ICT set C. Okay, well, all right, so maybe xni plus m delta didn't converge, go to a subsequence. You can find such a thing that converges. Okay? Then the distance from A to B, A is a point in the omega limit set, okay? B is something in C. The distance from A to B is equal to the limit of the distance from fn I of z, right? The fn of i's, these things converged to A, these things converge to B, and because the distance between pairwise here is less than epsilon over 2, the distance of the limit is less than or equal to epsilon over 2. Which means that the supremum as A ranges of the infimum as B ranges is less than or equal to epsilon over 2, which is less than epsilon. Okay? We can run a similar argument starting with a point B in my ICT set C. So given a point B in C, there's a sequence of natural numbers so that the things in my asymptotic pseudo-orbit approach B. Okay. Well, without loss of generality, fni minus m delta, the appropriate pre-images of, rather the appropriate images of z, right, the ni's ranging, it converges to some point A in omega z, right? And we'll play the same game to get to the fact that there is a z such that dh, the Hausdorff distance of omega of z to the set C is less than epsilon. Okay? And this holds for all epsilon, and so C is in the closure of omega f, and that establishes that, not omega f, W of f. So W of f closure is equal to C with shadowing. Okay, so what are some interesting reasons to think about this? Well, sorry, the corollary then was if you have shadowing and W of F is closed, then W of F is equal to ICT. I should say ICT, not just C. Okay. And another way of thinking about this is if you have shadowing and W of F is equal to ICT, then W is closed. So there's sort of two ways to take this to get some interesting information. So it's a well-known, I say well-known, it's a fact that if you have a map from the interval to itself, the collection of omega limit sets is closed in 2 to the x. This is a very intricate result of Bloch, Bruckner, Humke, and Schmidtall. So any map on the interval, if f from 0, 1 to 0, 1 is continuous, then the collection of omega limit sets of that map is closed. All right. And a similar result has been shown for maps on finite graphs. So even if your underlying space was a triad, or maybe something kind of goofy like this, right? If you had a map from this space to itself, then the omega limit set collection is closed in 2 to the x. And so what our result says is that if we have a finite graph and a map with shadowing, then the omega limit sets are perfectly characterized as the ICT sets. So this gives us a way to identify whether a set is the omega limit set of some point, which is a pretty powerful thing because it's an internal characterization. We don't have to calculate an omega limit set. All we have to do is address whether that set is a closed internally chain transitive set. All right, but we can also play this the other way. Okay, we know that some systems have shadowing and that the omega limit sets and ICT sets coincide. For example, shifts of finite type, we saw yesterday, they have shadowing. And we can establish without too much work that every omega limit set is an ICT set. And that tells us that then for shifts of finite type, the collection of omega limit sets is closed. This also holds for topologically hyperbolic maps and certain quadratic maps acting on their Julia sets. And so the corollary of this result is that for these sorts of systems, the collection of omega limit sets is closed. All right, so with our remaining half hour, I think what I'd like to talk about here is let's see if we can make this a bit more precise. Okay? So shadowing gets us here. Shadowing tells us that the closure of W is equal to ICT. Can we loosen that restriction? Okay. Can we find a form of shadowing which actually is equivalent to W closure equals ICT, right? Shadowing implies this characterization. Is there a form of shadowing that's equivalent? Okay. And what about just W equals ICT? That's a little bit of a stronger result. Okay? And the answer to all these questions is yes, and we'll see how far we get here. Okay. So in order to proceed, what we need to do is look at some variations of the shadowing property. And the first of these that I want to talk about is what's called orbital shadowing. So orbital shadowing is going to make use of the Hausdorff metric. So what we're going to do with orbital shadowing is we're going to have the setup is basically the same. For every epsilon greater than 0, there's a delta greater than 0, such that every delta pseudo-orbit, there is a point such that, and this is where it's different, rather than looking at the pairwise distances, we look at their distances of the sets. The orbit of X is close to the delta pseudo-orbit. So in orbital shadowing, we don't care about order. We don't care that X and Z naught are close together. We don't care that F of X and Z1 are close together. We don't care. Okay, so orbital shadowing is a little different. So for example, if say A, B, A, B, A, B is a periodic orbit in some space X, then the orbit BA, 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 BA orbitally shadows it. Okay. We see that these distances are quite large pairwise, but as sets, they're actually identical. right? And so the orbit's shadow. Okay? Okay. So it's clear on its face that orbital shadowing is a weaker property than shadowing, right? Shadowing tells us that we can find a point X so that Z0 and X are close together. Z1 and F1 of X, Z2 and F2 of X are all close together. And if they're point-wise close together, then they're set-wise close together. Being set-wise close together does not mean they are point-wise close together. So this is on its face a weaker property. Okay? However, it doesn't do what we need. It does not imply that omega of F closure is equal to ICT. Okay, and where's my example of this? Right. So as an example of that, where we have, sorry, there's my example. Okay, so the example I want to consider is, I want to consider, we haven't talked about them, but what I want to consider the subset of 0, 1 to the Z consisting of all sequences with no more than 1, 1. All sequences with at most 1, 1. Okay, so we're looking at, in other words, we're thinking about the set that looks like 0 to the minus infinity, 0 to infinity. We're looking at 0, dot, 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 1, 0, dot, 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 and all of the various shifts of that. Okay. So without going into a ton of detail on it, the picture for this, let me see if I can find somewhere decent to draw here. Let's unshare that and switch over to a different thing. All right, so if I were to draw this space, I would have the fixed point 0, 0 going in both directions. I would have here the point 1, 0 going that way, 0 going this way, where this is the central symbol. Okay? And then I would have a sequence of points, 0, 1, here's now my central symbol, 0, infinity, going that way, limiting this way. So this would be 0, 1, 0, central symbol that way. Okay, and then going here. And the dynamic of the map would be moving points along this way. Okay. So we talked yesterday about one-sided shift spaces. Two-sided shift spaces are sort of a similar sort of setup, and we have this point is fixed. All right, so this is a space that has orbital shadowing. And we can see that because a delta pseudoorbit does one of two things. A delta pseudoorbit, for a small enough delta, either starts somewhere and then stops here forever, or it starts somewhere, comes around here, gets really close to that, and then comes back around. So my delta pseudoorbits have a lot of different options, but they all either fill up a portion of the space or the whole space. Now, it's pretty easy to see that we can find an orbit that, at least with tolerance, does that same thing, right? If we start close enough to my fixed point here, then the orbit will, as a set, fill up most of the space just as well. All right. So that's sort of a sketch of the idea of why that should have that property. So let's come back to my other presentation here. All right. Now, if we want to get to our characterization, we have to be a little bit stronger than orbital shadowing. So let's define something called strong orbital shadowing. So a map F is going to have what we call strong orbital shadowing, provided that for every epsilon there's a delta, such that every delta pseudoorbit has a point X such that not only is the orbit of Z close to the orbit of X under the function as sets, but we also have that's true if we cut off the initial bunch of things. All right, so that same diagram that we had a minute ago, if we look at that, an orbit you know, looks like we start somewhere, we come along, 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 and eventually every orbit kind of gets in here and stays there. Okay. So orbits can fill up a lot of space, but if I start looking at the orbit of shifts of it, and I'm doing this for all n, then I start ignoring all of these things, right? So if I look at that, and we see that orbits for this situation don't fill space, but pseudo-orbits still do. Okay? So that situation, that system we just talked about, had the orbital shadowing property, but doesn't have the strong orbital shadowing because a lot of these space-filling properties of the orbits for that one are due to the initial parts of the orbit. So strong orbital shadowing is kind of taking an orbit as a set and it's sort of ignoring the sort of transient initial bits. Okay. All right. So strong orbital shadowing is weaker than shadowing still. You can see that without too much difficulty. And it's definitely stronger than orbital shadowing. And in fact, it's, in a very real sense, sort of right on the nose. And before we get to a proof of that, I'm going to talk about yet another kind of shadowing, which we will eventually get tired of hearing about. The next kind of shadowing is called eventual shadowing. Okay? So what we're going to do here is we're going to take an epsilon and a delta, that any pseudo-orbit, there might be a point that doesn't shadow it. Rather, the initial parts might be bad enough that they make it not shadowable, but it's eventually shadowable. There's some point that, so here's my pseudo-orbit, right? It's doing some things like this. There are these small jumps. Okay, and those jumps, you know, they stay some size. And we're eventually shadowable if there's some point z that does some stuff that's completely unrelated for a while, but then eventually comes close and stays close. Right? So initially there are large gaps, but then eventually they are close. So eventual shadowing has, space has the system has the eventual shadowing property if it has this property here as written. All right. So eventual shadowing is also weaker than shadowing, right? If we had shadowing, then this is for all I in omega, which is regular shadowing. And so this is obviously weaker than shadowing. Okay. And now a theorem of Chris Good, a colleague of mine from the University of Birmingham in the UK, and I a few years ago proved that if F is a dynamical system with the eventual shadowing property, then the closure of W is equal to ICT. Okay? And we also note that there are systems W with W closure equals ICT without the eventual shadowing property. Okay? We also proved that if you have the strong orbital shadowing property, then the closure of W is equal to ICT of F. But there are systems with W closure equal ICT without the strong orbital shadowing property. So neither of these properties is quite right. They both imply the correct thing, but neither is equivalent to it. Right? Both eventual shadowing and strong orbital shadowing both demonstrate that omega or W closure is equal to ICT. Okay. So before we proceed too far, we know that the closure of W is a subset of ICT. So all that's needed in these theorems is to show that that every ICT set is in the closure of W. Okay. And the proof of both of these properties is essentially the same argument that we had for shadowing. There's some tweaks along the way, but the proof is very, 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 very similar. Okay. All right, so can we do a little bit better? And the answer is yes, by combining the two. So if we have the eventual strong orbital shadowing property, it's the same as the other ones. Okay, we have every epsilon, there exists a delta such that for any delta pseudo-orbit, there's a point z and a k such that two orbits setwise agree, or setwise are close for n beyond some point. Okay? So we're really just combining these two notions. Okay? So schematically, we have shadowing sort of here at the bottom. It's very strong. It implies eventual shadowing. Shadowing implies strong orbital shadowing. And both of these together give us eventual strong orbital shadowing. Okay. And it turns out that that is the right property. It's equivalent to something called the cofinal orbital shadowing property. Eventual means that there's some point at which it starts orbitally shadowing. Cofinal orbital shadowing property is essentially the same thing. It's just saying that there's some point beyond which they're orbitally shadowing. And the theorem that brings this all together is that if F is a dynamical system on a compact metric space X, then we have the following three equivalent things. If F is eventually strong orbital shadowing, then F is cofinal orbital shadowing, and then the closure of W is equal to ICT. Okay. And again, the proofs of these ideas are not so different from the techniques we just went through. Okay. We're going to do a lot of the same things, right? To show that W of F closure is ICT, we start with, we have W1 is equal to omega of some x1, W2 is equal to omega of some x2, and we eventually get to some set C, which is, we know is ICT, and we need to show that it's an omega limit set, and we kind of play these same games, okay? There's a little bit of work to do, but it's a lot of the same ideas. All right, so we have this notion of a way in which we can tell that the closure of W is equal to ICT. Okay. So this wraps up that question of, can we characterize that property? Now, of course, the auxiliary question, the additional question is, can we characterize W equals ICT? And we'd like the answer for that to be yes as well. This one's a little bit tougher to get our hands on. And so we need to look a little bit something a little different here. All right, so a few things of note. Right, we know that in some spaces W is closed. So for interval maps, for example, W equals ICT if and only if F has eventual strong shadowing, strong orbital shadowing. For finite graphs, okay? But for lots of other spaces, WF is not closed in general, right? It might be for a given F, but there might be Fs for which it isn't. So we can't hang on that. So how do we get at the question of characterizing W equals ICT? So dropping that closure. When do we know that every ICT set is an omega limit set and not a limit of omega limit sets? Okay, to get at that, we need to have the notion of an asymptotic pseudoorbit, which we had kind of already addressed earlier when we were proving some things. So a sequence is an asymptotic pseudoorbit if the distance between xi plus 1 and the image of xi goes to 0 as we go along. So we might have something that starts out being a very bad pseudoorbit, like with big gaps here. Again. But then as we go, the gaps get smaller, 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 smaller. Something like this might be an asymptotic pseudoorbit, right? Where we have large distances. Here we go. Large, smaller, smaller, smaller. All right. So a system has what we call asymptotic shadowing. Sometimes it's called limit shadowing, provided that for each asymptotic pseudoorbit, there's a point that asymptotically shadows it. So not only do we have a point, an orbit, a pseudoorbit that's getting closer and closer and closer to behaving like an orbit, but not being an orbit, then we have an orbit that gets closer and closer and closer to that pseudoorbit. Now this is a big property. It's a very strong property, okay? But it's strong enough in sort of the right way, and that Barwell, Good, and Naproja-Raines, and one of the papers we mentioned earlier, proved that if you have asymptotic shadowing, then W is equal to ICT. Okay. Again, it's a lot of the same ideas here. This one's even more straightforward, right? If you take that C in ICT, you build up that asymptotic pseudoorbit within it that we talked about. This, you write down AI with the omega limit set of AI equals C, and then just pick a point Z that asymptotically shadows it. So if Z asymptotically shadows AI, then omega of Z is equal to C, and you get exactly where you need to be. So certainly asymptotic shadowing is enough. But as with shadowing, it turns out that that's far too strong. All right, so there are systems here which have WF equals ICT of F that don't have asymptotic shadowing. So for example, yeah, all right, let's draw one real quick here. If I take here, let's draw some axes here. Let's look at, here's positive 1, here's negative 1, positive 1, negative 1. Let's take a function that is, on the one hand, this is the slope to tent map, and then on the other side is acting like the square root of negative x. And this is 2x, and this is 2 minus 2x. Okay. So looking at this, with a little bit of work, we can show that this has W equals ICT of F. Okay. And the reason for that is because an ICT set either lives entirely over here or is just the point 1, right? So ICT is equal to ICT of the tent map. Let's call that one T. Union, the very boring set, minus 1. And of course, we see that, sure, this thing here had the property that ICT was equal to W, and that's definitely the omega limit set of itself because it's a fixed point. Right? And this thing does not have the asymptotic shadowing property because we have asymptotic pseudo-orbits that start over here and end up over here, but no orbit can possibly do that. All right, so we need to do some things, okay? And we're going to follow that same progression we did for shadowing. So let's define the asymptotic orbital shadowing property. And this is the property that for every asymptotic pseudo-orbit, there's a point z such that for any epsilon greater than 0, there's an n such that the sets are within epsilon of each other, right? So rather than, instead of taking the distance of xi and fi of z goes to 0, we're looking at this distance of the sets going to 0. Okay. And let's see what's next. So the asymptotic strong orbital shadowing property is going to be the same thing. We're just going to say, there is a k such that that happens for all n bigger than or equal to k. All right, the orbital limit shadowing is a property due to Pelyugan. It's saying that for every asymptotic pseudo-orbit, there's a point z, so that the omega limit set of that z is equal to the omega limit of the asymptotic pseudo-orbit. And it turns out that all 4 of these things are actually equivalent. The proof techniques are very, very, very similar to what we worked through, but we have this very nice equivalence of when W of F is equal to ICT of F. W is equal to ICT if F has the asymptotic orbital shadowing property, which it turns out is equivalent to the asymptotic strong orbital shadowing property and the orbital limit shadowing property. So when we have the asymptotic, the word strong isn't strictly necessary, but it doesn't hurt to have it in there for the sake of a parallel construction. So that's what I wanted to get through today. I'm happy to open up to questions now. Just as a little heads up for tomorrow. Tomorrow we're going to address the question of, given a topological space, do I expect a map to have shadowing? There exist topological spaces where most maps have the shadowing property. We're going to explore that idea tomorrow. So let me stop sharing the screen and open up to questions if there are any.
¿Hay preguntas, chicos? Parece que sí. Can you see the chat?
I can see it now. I see one question in there. The set / omega x, not the same as / omega x. So omega x is, what are you using capital omega x for there? I've seen that denote several things. I want to make sure we're talking about the same thing. Are we talking about the non-wandering set or? Okay, so I'll tackle this other question. To what extent are these techniques useful to provide conjugacies between F and a perturbation of F? Oh, that's a really good question. And the answer to this is what we talked about today, significantly less so. The shadowing property allows us to talk about, the shadowing property is very related to the notion of stability, which is what you're talking about here, where we have conjugacies between F and a perturbation of F, in the sense that a pseudo-orbit we can think about as an orbit for a perturbation of F. And so if we're thinking about shadowing, shadowing tells us that at least the orbits of perturbations are close to the orbits of F, and that can give us a way to construct maybe a conjugacy. Of course, we're just knowing this orbit-wise, it doesn't really give a great perfect way, because given a pseudo-orbit, an orbit for F prime, say a map close to F, there might be lots of points who shadow it. So it doesn't provide a perfect translation, but it gives us a way in. Now, there are spaces that have something called the unique shadowing property, and this would give us a better way to take an orbit for the perturbation and pick a single point that should be the right thing. All right, so hopefully that answers that question a little bit. It's not a perfect correlation between stability and shadowing, but there are some relationships. All right, so let's see. The set of y in x such that there's a sequence xi, I in x, and an increasing sequence. So sequence xi in x and an increasing sequence ni, so that fni of xi converges to y. So that's an interesting question. I do not know the answer to that. That's a really good question. So here, and Gerardo was asking to look at, rather than looking at f of a single point, we're suggesting looking at f of x1, f squared of x2, so on and so forth. That's not something I'm actually familiar with, and I would be very interested to learn more about that. I would think a lot of the same techniques could go through on there, but I would be really just kind of making things up if I tried to make some guesses there. So that's a really interesting thing. It's not something I've seen before, but yeah, I would like to learn more about that. So thank you for your question. I wish I had better answers for you there.
¿Más preguntas, chicos? Well, I have a question. Do you have any results of ICT sets with not omega limit sets, but alpha limit sets?
We do have some of those things. One of Chris Good's students, Joel, has done a fair bit of work with that. I've worked a little bit with that. And we can say a lot of the same things there. One of the big difficulties being that the notion of what an alpha limit set is a bit fuzzy. So an alpha limit set, if we have a homomorphism, an alpha limit set is the same as an omega limit set for the inverse function, right? So if f is a homomorphism, we can talk about the omega limit sets for f inverse versus the alpha limit sets for f, and we can run a lot of the same things through there. If f is not a homomorphism, we run into some issues with continuity, and if f isn't even one-to-one, then we have choices.
Yeah.
And there are some things we can say, but we have to be really careful about what we call the alpha limit set. And without going into a lot of detail, there are results. They are not quite as satisfying because of that.
Okay.
So I can definitely send you a paper with some results on that front. They're, like I said, not quite as satisfying, but there are relations between alpha limit sets and ICT sets.
Okay, okay.
Provided we're thinking about the right kind of ICT sets. All right, so another question from Gerardo here. How far can you go with this orbital shadowing variations? Can we include asyndetically orbital shadowing, say, or syndetically? Okay. So there is a very rich theory of variations of shadowing. I've written a few results on it. There have been a lot by Piotr Oproha and a few of the other guys in Poland and other countries over there. Things that come up a lot, syndetically less so, but thick, right? Thick, a set of natural numbers is thick if it contains arbitrarily long intervals, or if writing it a different way, if it's co-syndetic, right? If it intersects, not co-syndetic, if it intersects every syndetic set. And there's a lot to be said under fairly mild conditions that I don't recall off the top of my head, where thick shadowing, which is the notion that a pseudo-orbit can be shadowed on for a thick set of indices. So there are going to be some indices where it's way off, but on a thick set of indices, then that should be equivalent to regular shadowing under appropriate, relatively mild conditions. And then we can do other things like, instead of talking about a delta pseudo-orbit, we can talk about a thick delta pseudo-orbit, where we have a sequence where xi plus 1 and f of xi are close, but only sort of intermittently on a thick set, or a set of, say, positive lower density, or things like this. There's a whole lot about that. And you can build a whole hierarchy of different kinds of shadowing properties from that notion. And under certain circumstances, there are some equivalences. I'm not familiar, I haven't looked at it much, looking at whether you can draw inferences from those variations to the omega limit set stuff that I talked about today, but it's definitely something that's worth looking at. But I don't have any answers for you today because you keep asking questions that are really great and that I've not had a chance to think on. So thank you.
Okay. Bueno, pues le agradecemos a Jonathan y pues nos vemos mañana. Thank you very much, Jonathan.
No, thank you, everyone. Thank you all for your questions. Thanks for your attention, and I will speak with you guys tomorrow. Thanks so much, everybody.
See you tomorrow. Bye.